Our eyes define the way we see the world. For thousands of years, men fought and died in complete darkness. But in the mid-20th century, something changed. A series of innovations converged, redefining how nighttime operations are conducted. These are night vision goggles, and this is how they work. For decades, the ability to conduct military operations at night has been recognized as an important goal, allowing special forces to see and act in environments once deemed too dangerous or even impossible. Image intensification technology has been pivotal in advancing this goal. The idea is simple. This is the electromagnetic spectrum, covering every wavelength of light, from low-energy radio waves to high-energy X-rays and gamma rays. Only a narrow sliver of this spectrum is visible to the naked eye. However, at night, the near-infrared spectrum contains roughly 10 times more light than the visible spectrum. Like visible light, this infrared light primarily comes from moonlight and atmospheric glow. These sources flood the environment in a blanket of energy that is only partially visible to the naked eye, but that can be exploited and converted into visible light. During the US wars in the Middle East, nods became essential for coordinating aviators with ground forces. These units used infrared illuminators to mark friendly positions and weapon-mounted IR lasers to designate targets, which could then be confirmed by aircraft overhead. Because these tools operated in the infrared spectrum, they were invisible to the naked eye, allowing friendly forces to communicate and coordinate without the enemy's awareness. The first real breakthrough came in the 1930s as a result of early research in the television industry and the development of an image tube that can convert infrared light into visible images. Recognizing the military significance, the US Army raced to create its own infrared systems, culminating in devices like the US Sniperscope, deployed at the end of World War II. Simultaneously, the Germans pursued similar technologies. This is an example of a prototype nighttime scope developed by the US. Classified as an active night vision device, it couldn't detect ambient IR light on its own and needed an external source to illuminate the target area. This infrared light is reflected off the environment and focused through a series of optical lenses and onto the image tube. The image tube consists of a photocathode, a cone-shaped anode, and a phosphor screen. When a photon strikes the photocathode material, its energy is absorbed, enabling an electron to overcome its binding energy. These electrons are then focused and accelerated through the anode, gaining energy before colliding with the phosphor screen. Upon impact, the electron's kinetic energy is transferred to the phosphor molecules, causing them to become excited. When these molecules return to their original state, they release this energy as green visible light, which is then focused and flipped upright through the ocular lens to the user's eye. By the late 1950s, Army engineers had successfully developed the first light amplifying tubes. These tubes incorporated a more sensitive photocathode and optimized the electron acceleration process, generating brighter, higher contrast images solely from available ambient light. By developing smaller, more powerful image intensifiers, engineers were able to create a range of devices that came to define the first generation of night vision technology. This is the AN PVS-2 Starlight Scope, the first Gen 1 night vision device fielded by US troops in Vietnam and the first to utilize the new Intensifier tubes. It's powered by a 3-stage image intensification assembly that incorporates 3 Gen 1 Intensifier tubes connected in series via fiber optic junction plates. With each amplifying the output of the previous, this system could amplify light by a factor of 1,000. Most importantly, this could all be accomplished without the use of a floodlight and could be powered solely off onboard batteries. Although too costly for broad deployment and too cumbersome for most applications, including their intended use as a weapon optic, these first-generation devices still accomplished 2 important things. They satisfied an urgent need for nighttime surveillance for troops in Vietnam and proved that passive image intensification technology could work. Night vision research accelerated in the 1960s under high-priority directives from the US government, leading to the development of a thin glass wafer that would usher in the second generation of image intensification. Engineers applied the same fiber optic manufacturing processes from Gen 1 to create a thin glass wafer embedded with thousands of angled, hollow channels, specifically designed to promote electron collisions. The lead oxide glass has a high secondary electron emission coefficient, meaning that when an electron strikes the channel wall, it releases additional electrons. This process is known as cascaded secondary emissions and is the reason the microchannel plate is such an excellent electron multiplier. The voltage applied to the MCP could also be adjusted. Lowering the voltage in bright conditions reduces electron multiplication, preventing overexposure. Conversely, increasing the voltage in low light scenarios enhances amplification. This is a fully assembled Generation 2 image intensifier tube. The microchannel plate sits directly between the photocathode and the phosphor screen. Measuring less than 1 millimeter thick, the MCP enables a size reduction of up to 40% over prior generations, while consuming considerably less energy. In addition to an improved photocathode, the phosphor was now deposited directly onto a fiber optic inverter. This is a coherent fiber optic bundle that is physically twisted 180 degrees to reorient the image. Because the image arrives upright at the eyepiece can now be simpler and lighter. With vast improvements, second-gen intensifier tubes allowed the AN PVS-5 to become the first practical head-mounted night vision device adopted by ground forces and aviators. Each eye was fed by its own image intensifier, providing binocular vision and boosting ambient light by about 20,000 times, allowing aviators of fixed wing and helicopters to conduct missions during ambient lighting conditions that would have been impossible with unaided vision. Operation Eagle Claw stands as arguably the first complex, multi-aircraft, long-range night infiltration mission where the performance of night vision goggles was absolutely central to the success or failure of the mission. This mission, launched on April 24, 1980, was a critical effort by the United States Armed Forces to rescue 52 American diplomats held captive in Iran. The aviation component involved a complex rendezvous at a desolate salt flat approximately 200 miles southeast of Tehran, where 8 United States Navy RH-53D Sea Stallion helicopters were to meet 6 C-130 aircraft. The Sea Stallions would refuel and pick up combat troops and equipment before flying to a mountainous area closer to Tehran, where the rescue raid would be launched the following night. Eagle Claw demanded highly coordinated, low-altitude flight by multiple helicopters over vast distances in challenging terrain, all while relying heavily on the AN PVS-5 goggles for navigation. 3 weeks prior, covert CIA operatives flew into the landing zone and installed remotely operated infrared lights and IR strobes, outlining the landing site for pilots equipped with NVGs. At 10:47 p.m. local time, the first MC-130 successfully landed at Desert 1 under blacked out conditions using the infrared lights as a guide. During their flight to Desert 1, a handful of helicopters got caught in a large-scale regional sandstorm that drastically lowered the already poor visibility and caused problems for the Sea Stallions. One of the 8 helicopters had to make an emergency landing and was subsequently abandoned in the desert, while another had to turn around due to loss of electrical power. The remaining 6 helicopters arrived over an hour behind schedule, with one arriving with severe mechanical problems. Unfortunately, what followed was a series of operational planning and technical failures that ultimately resulted in the loss of 8 servicemen and no hostages rescued.
This is the core of the tragedy. First impressions might suggest that this is simply the wreckage of the giant C-130 transport plane. But this is the entire rotor assembly of one of the American helicopters that were involved in the rescue attempt. It was parked over here, and it was when it took off on a mistaken bearing that it sliced into the Hercules plane.
While the AN PVS-5 was not the cause of the mission's collapse, its technological shortcomings combined with insufficient pilot training and the harsh environmental conditions were critical factors. The AN PVS-5 was not designed specifically for aviation and led to significant challenges. Cockpit lights interfered with the goggle's spectral response, while the tube's 40-degree field of view induced spatial disorientation, worsened by a housing that blocked all peripheral vision. And most critically, pilots underwent very little nighttime training, nowhere near enough time to get comfortable with the technological limitations. These factors had a massive impact on pilot confidence. However, emerging threats posed by low-cost, shoulder-fired weapons meant that the key to survivability would be flying low and flying at night, so aviators got creative. They started off by covering certain cockpit lights with black tape and eventually cut away the lower half of the housing, restoring some peripheral cockpit awareness. By 1982, tests were already underway for a suitable replacement specifically designed for aviation. This development culminated in the AN AVS-6. It mounted to a single point on the pilot's helmet, eliminating the need for a full face mask and allowing near full peripheral vision, and featured a flip-up design, enabling pilots to quickly transition between aided and unaided vision. Most importantly, the AN AVS-6 featured a brand new 3rd-generation image intensifier tube. The main improvement from Gen 2 to Gen 3 came from the introduction of a gallium arsenide photocathode, which is far more efficient at converting photons into electrons, especially in the near-infrared spectrum. Gallium arsenide photocathodes are engineered with a negative electron affinity. This means that once a photon strikes the photocathode and ejects an electron, the electron has a much easier time of escaping the material. The result is a tube that is about 2 to 3 times more sensitive in low light and offers double the light amplification when compared to Gen 2. Making it the first truly effective starlight-only tube. This heightened sensitivity did come at a cost. During operation, residual gas molecules inside the vacuum tube could become ionized and subsequently collide with the photocathode, degrading it over time. To mitigate ion damage, a razor-thin aluminum oxide film, approximately 30 angstroms thick, was applied over the input of the microchannel plate. This protective film acts as a barrier, preventing ions from escaping the MCP and striking the photocathode. While some electrons are absorbed by the thin film, reducing throughput and causing occasional ghosting, the overall gains in low light performance far outweigh these minor drawbacks. This is the AN-PVS-7. It emerged as a successor to the AN-PVS-5 for ground forces and featured a single tube configuration, making it cost competitive and ideal for broad deployment. The design consists of either a Gen 2 or Gen 3 image intensifier tube, followed by a mirrored array that projects the amplified image to each eye. This is a biocular device. Each eye was fed the same image, meaning all stereoscopic depth perception was lost, a drawback that impacted some occupations more than others. Undersecretary of the Army James R. Ambrose was concerned about balancing cost, performance, and the practical value of investing in third-generation night vision technology. To address this, in 1987, comprehensive field tests were conducted worldwide. Researchers measured global night irradiance, correlated the spectral reflectance of Eastern Bloc uniforms with irradiance data, carried out numerous field tests, and completed a full life cycle cost analysis. The results were clear. Gen 2 devices were found to be more sensitive in the visible light range, while Gen 3 had a significantly greater sensitivity in the near-infrared spectrum, aligning them closer to the night sky irradiance that was measured. This difference proved to be crucial for combat effectiveness. The near-infrared sensitivity of Gen 3 enabled the detection of enemy targets at up to 150 meters, a 50% improvement over Gen 2, as Eastern Bloc uniforms were also more reflective in the near-infrared spectrum. Across all lighting conditions, Gen 3 devices consistently outperformed Gen 2 by between 20 and 30%. Reliability data was also significant. While earlier estimates for Gen 2 reliability were skewed by non-tube related issues, Gen 2 tubes had a real mean time to failure of approximately 2,000 hours. Gen 3, with its ion barrier, was estimated to last around 10,000 hours. This study resulted in a two-pronged rollout. Gen 2 and biocular devices would continue to be used by support personnel, mechanics, and other roles where high sensitivity and depth perception were not critical, whereas high-risk combat personnel, special forces, and aviators would adopt the more advanced third-generation technology. Beginning in the 90s, night vision technology entered a new phase of refinement. Standardization in tube design enabled manufacturers to offer specialized equipment that was adaptable and customizable, such as white phosphor intensifier tubes. Introduced as an alternative to the long-established green phosphors, white phosphor provides a cooler-toned grayscale image that some find to be more natural. Whereas phosphor color comes down to preference, other technologies have improved performance. Filmless and thin film designs eliminated the ion barrier from the MCP, made possible by ultra-high vacuum housings that reduced residual gases that could then ionize. New ways to fuse digital and thermal solutions also emerged, as technology and material science advanced. However, despite decades of technological advancements, some fundamental limitations persisted. Most notably, the 40-degree field of view, which has proved the most challenging. Widening the field of view by using a larger lens or expanding the size of the image tube seems like an obvious evolution, but it instead introduces a series of cascading problems. Field of view, resolution, and cost are tightly coupled parameters. Resolution, measured in line pairs per millimeter, is ultimately limited by the physical properties and geometry of the microchannel plate. More channels results in finer details that can be resolved, but this has reached its practical limitations at its current size. However, expanding the diameter of the tube spreads the same amount of light over a larger surface area, lowering the signal-to-noise ratio and creating a grainier image, all while being significantly more expensive to manufacture with lower yields and higher failure rates. Alternatively, a wider lens distributes a larger area over a fixed resolution, making distant objects appear blurrier, and introduces pincushion distortion, which is disorienting. Expensive and complex lens assemblies are needed to control for these effects, but they still add weight and diminish the image by absorbing light. The result is a heavier, more power-hungry, and exponentially more expensive system for only a modest gain in FOV. That is, unless you could somehow develop a night vision device that incorporates more than 2 image tubes. Well, that's exactly what the US government chose to do. This is the AN AVS-10, developed in the late 90s by the US military with the explicit goal of providing aviators with heightened peripheral awareness. It was the first true panoramic night vision device, battle-tested and proven by airmen. The specialized housing feeds each eye with 2 third-gen image tubes, fused through a single ocular lens, granting the user a 95-degree field of view. The result is an unprecedented level of situational awareness, but also cost, weight, and complexity, making them truly a specialized piece of equipment. Pilots of low-flying fixed-wing aircraft, such as the A-10, were the first to get access to these quad nods, but eventually they ended up in the hands of Special Operation Ground Forces. The L3 Harris GPNVG-18 further refined this concept and were quickly adopted. While not ideal for every scenario, these goggles undeniably aided Special Operation Forces, including those involved in the mission that ultimately brought down Osama bin Laden.